Okay, welcome to lesson 43. So we have been plotting our bivariate quantitative data into a scatter plot fitting a line, and now we're going to go look at performing a t-test for the slope coefficient. So what this gets at is this explanatory variable useful in making predictions about the response variable? Hopefully it is, otherwise why use it? But you know, it isn't always. So we're going to look at performing the test. So here, a lot of times we will ask ourselves, hey, is the relationship between A and B significant? Is A useful in explaining B? If I know something about A, does it tell me something about B? That kind of thing. Be careful. You don't want to use causal language. You don't want to say, hey, does A cause B? Unless you know that a randomized experiment was performed. So, for example, because we really love this one, we're looking at the GPA example again. We have a small college and they want to know if the graduating high school GPA of their students is a useful predictor for their first year college GPA. So at the end of their first year, their GPA there. So they take a random sample of 10 students, admittedly not a lot. A lot of it is just so we can show you a small scale example here. So we want to investigate how we can actually answer their question. Can we look at, like, hey, does high school GPA help explain the college GPA? So what we're going to use a t-test on the slope. So in the last lesson, lesson 42, I think, I don't know, I can't count. We did a confidence interval for B1. Now we're going to do a t-test. So it was a t procedure confidence interval for B1. Now we're going to do a t-test. So that's a hypothesis test. Oops, I can spell test for beta 1. So beta 1. If I said B, ignore that. So when we want to use this, we want to test whether the explanatory variable helps to explain any change. It does not mean that we are saying it causes it. Just does knowing some information about what they had in high school, does that help inform us what they got in college? That kind of idea. So what our conditions, they're going to be pretty much the same as they were for the confidence interval for the slope. We want to know we have a representative sample. Easiest way to get there is with a random sample. And then we want to make sure that we meet the 4 conditions. So we'll look at the residuals in particular here. So linearity. So if we fit a line to the data, is a line appropriate? Or should we be using a curve? Independence. Are the observations reasonably independent from one another? You don't want to have related observations in your sample. Are they normally distributed? So if you fit a line, if you were to take a slice at any point on that line, are the points roughly normally distributed around that line? And then constant variance, is the spread roughly the same around the line for all values of x? So our null and alternative hypotheses, they will shift just a little bit. We have a new parameter we're looking at. So our slope for this week, we're doing simple linear regression. So simple just means we have one explanatory variable, which hopefully is a hint at next week. Multiple linear regression means we have more than one explanatory. So when we have one explanatory variable, beta 1 is it. And by default, we'll assume, nope, the explanatory is not useful in explaining it. There is no relationship between x and y. So the null will be saying, nope, knowing your high school, the high school GPA of a student does not give me any additional information, does not help me predict their college GPA. The alternative, and the alternative is always going to be two-sided, always, is going to be there is a relationship. So yes, high school GPA is useful in predicting the college GPA. So once you determined you want to go ahead and test the slope and you've made sure your conditions are met, you've written out your hypotheses, our test statistic is going to be a t statistic, which implies that we are going to be looking at a t-table or using R to find our p-value. So note here, so what we saw in the sample, so our sample statistic, so observed sample statistic, so this is usually you'll get from our output, that's your estimate for the slope. Your null value, so by default we assume that beta is equal to 0, and then divided by this standard error. Once again, please don't do this to yourself and calculate the standard error by hand unless you really like doing like algebra, but take the standard error from the output. It makes your life a lot easier. So once you've calculated your test statistic, then you can go ahead, you can either use R to find the p-value, and or you could use your t-table. Do remember, it's a two-sided test, so if you find a one-sided probability, you have to multiply by 2. And if you're using like a table, or R, the degrees of freedom for this test statistic is going to be your sample size minus the number of parameters. So you put one explanatory variable in, so just one, plus another one. So what's great, so everything you need to calculate is here. Everything you need to check is right there. So you take this information, so this divided by that should equal that, and then this is your two-sided p-value. So if I wanted to look at my test here, so I'm going to look where it says coefficients. Intercept always goes with the y-intercept. High school GPA, that's the name of my explanatory variable, so this is B1, this is standard error of B1. Note that I'm just, my estimate for this, my standard error for this, they line up. My t statistic here is 4.006. My p-value is 0.00392. So the p-value is pretty small. My degrees of freedom, they were equal to 8, so remember 10 minus, I had one explanatory variable, plus 1 is just 10 minus 2, that's 8. What's also great is you can find it right there. R will calculate that for you. So then I can go ahead, I can do a two-part conclusion for this hypothesis test. It will look very similar in structure. Well, actually, we're going to go through the whole thing here. So going through all the steps here, is high school GPA useful in predicting average college GPA? So if I want to write this, beta 1, and remember, beta 1, do not write B1. We will get you. It must be the Greek letter beta. Even if you're like beta, at least do that. No, like make sure that we know that it's beta, the Greek letter beta. It cannot be the letter B. The letter B is a different thing for us. So it must be a beta. So you should either type it as a beta or have the word beta. So beta 1, always have an equal sign in the null hypothesis. And then is equal to 0. So layman's terms here is high school GPA, not useful in predicting college GPA. The alternative, it's always going to be two-sided. Beta 1 is not equal to 0. So it's basically the opposite of this, that high school GPA is useful in predicting college GPA. Significance level, it's good to keep track. Remember, if we don't give it to you, you can always clarify with us, hey, it doesn't say this, can I assume? Default is usually going to be 0.05. You are always welcome to clarify with us. We usually, if we don't include it, you can assume 0.05 or contact us. And then conditions for inference. So we want to know that sample of 10 students that we used to create this least square regression line Was it a random sample? So that comes from here. Data are from a random sample of 10 students. Yes. So random sample. So we can assume, hopefully, our sample of 10 students is representative of the whole student population. This is one of those issues where just having 10, it might be pretty problematic. I would hazard a guess that a lot of people are not being represented in a sample of 10. So then residuals, they need to indicate the 4 conditions are met. So we're going to go ahead, I believe, yes. Well, no. We have, oops. So this is from before. So yes, from before we had random scatter. So residuals plot, random scatter. And then you could also use that normal QQ plot. I can provide the code to make that. As long as the points roughly fit the line, it indicates that yes, the normality conditions roughly met. And as for independence, as long as you can assume that these students are independent from one another, you're probably okay. Now, if they've been classmates and or twins like forever, you may want to hesitate. But from student to student, unless they all came from the same place, you're probably okay. So I want to visualize what the hypotheses are actually saying. So if the null is true and high school GPA is not useful at all in predicting the college GPA, I can use just a flat line to estimate. So if I knew high school GPA and I knew the college GPA and high school GPA wasn't useful, and I had to guess somebody's college GPA, I would just guess the average college GPA of the sample. That would be my best guess. A flat line is good enough. Looking here, it honestly doesn't look very good. It doesn't fit those points very well. The alternative, which usually is what we hope is true, is a flat line is not good enough. No, like high school, knowing their high school GPA gives me information. So here, if I know they have a 3.2, my guess for their college GPA is different than if I know they had a 3.8. That kind of idea. Versus here, if they had a 3.2, I'm still going to guess the average college GPA. If they had a 3.8, I'd guess the average college GPA. I'm not going to use information about high school GPA to make my estimate. So chances are, just at a glance, these two lines, it looks like this one fits a whole lot better than the other one. But we'll see. It's not just does it fit better, but does it fit better enough? So we'll get there. So we're going to fill this out. This is a 2-part conclusion. So here, here's my estimate, my standard error, my t statistic. So it says t value. Oops. Just know that's my t-test statistic, and then my p-value. So looking here, so my t-statistic was 4.006. My degrees of freedom are 8, because it's 10 minus 1 minus 1. My p-value is 0.00392. So just plugging into here, it's a 2-sided p-value, 0.00392. Note that if you use the t-table, you could say, hey, a two-sided p-value between blank and blank. That would be acceptable because with the t-table, usually you won't get more than a range of values. It won't be more precise than that. So I like to fill this part out first. You don't have to. It's a t-statistic equal to 4.006. Degrees of freedom 8. Two-sided p-value of 0.00392 at the 0.05 significance level. So I compare here. If your p-value is smaller, you reject. So I'm going to reject. So we reject the null hypothesis at the 0.05 significance level, and then I gave all this information here. So no matter what, we're looking to know if you rejected the null, what the significance level is, and we will want the p-value. This other stuff is preferred, but these other things, these three things, they're key. So then, if I want to write up the, describe the strength of evidence in context of the alternative, I would say, looking at this p-value, it's pretty small, so very strong evidence. You could also say convincing, that would be fine. So very strong evidence that whatever the explanatory is, so high school GPA. Oops. I can spell school sometimes. Oops. That's embarrassing. High school GPA is a significant predictor of college GPA. Sorry, sometimes the screen's so touchy when I touch it. College GPA. And you could be more specific, first year college GPA at this small university, probably in this given year. So yeah, this is my first part. This is my second part. So if we ask for a two-part conclusion, we want to know if you rejected and why. In the second part, we want to know how strong is your evidence and the alternative in context. If you don't give us context, that is something that's major. The context is huge. You don't want to say there's very strong evidence that X is a significant predictor of Y, because we're going to ask immediately as a follow-up, what is X and what is Y? So that would be my two-part conclusion here. And so you might have seen that's it for this one. So that was lesson 43. And then we're going to get into using this line for predictions, types of predictions, and some other issues.